Thank you. Thank you. Thanks for the invitation to speak here. It's a nice opportunity to speak in front of people I enjoy about something I enjoy. So the talk is split into 4 parts. First, we'll recall what are Wang tiles, and we will present 3 important examples. And then we will present the metallic mean Wang tiles, very nice set of tiles, family of Wang tiles, in fact. And then we will define the stone inflations out of them, which construct Rauzy fractals. And then some open questions. So it all started with a paper by Wang in 1961. So he presented 3 shapes that are now called Wang tiles. So a Wang tile is a square with labeled edges, and you want to tile the plane in such a way that if you put 2 squares side to side, they share the same label on the same edge. So here they give an example of 3 squares, A, B, C, with their labels. And then he noticed that you can glue the tiles like this, A, B, C, A, B, and B, C, A, in such a way that the labels match. Because between A and B is 2, between B and C is 3, and so on. And vertically as well, it works. And then if we look outside, we see labels 3, 5, 3, 5, 4, 3, 5, 4, and then 1, 3, 2, 1, 3, 2, which allows to repeat this 3 by 3 square and tile the plane periodically. So the question he asked was, well, if I have a cyclic rectangle, then it tiles the plane, but if I tile the plane with the tiles, by translation, do I necessarily have a cyclic rectangle? The answer turned out to be false. And this opened a field and many contributions that are gathered in these 4 books and many more about aperiodic tilings and so on. So if I restrict to Wang tiles, aperiodic set of Wang tiles, we can see that there are kind of 2 types of Wang tiles. So Berger was a student of Wang, so he found a substitutive set of Wang tiles, which are aperiodic. And then Knut, in the volume 1 of the Art of Computer Programming, at the very end in the appendix, he reduces the number of tiles by doing some simplification. He reduced it to 92 tiles. And then Robinson simplified it. And then Aman and Chandrao. So all of these are substitutive. And then on the other side here, you have the Carey and Kulik set of tiles. So Carey found 14, Kulik simplified it to 13. So these are very different because they are positive entropy. And the way they are defined is that the matching rules satisfy equations. So so it's back. So that's the setup. And then Jean et Rao in 2015, they also showed that they tested all examples. In fact, they tested with computer exploration that all tiles, all set of 10 or less tile, either they tile the plane periodically or either they don't tile at all. So the example they found at 11 was the smallest example in size. So today in blue, we will see a little bit more those 3 examples. Right now, we start with Carey. So these are the 14 tiles proposed by Carey. So each tile satisfies an equation like this, relating the matching rules like the size A, B, C, D, will satisfy Q times B plus C is equal to D plus A. You can see B as an input, D as an output, and C a left carry, and A right carry to make the equation work. So this is very nice because if you glue 2 such squares together, you can sum the equation. You will see that carries cancel, and you obtain an equation of the outside box. And what you see is that you multiply the average of the top, and you obtain as output an average. The average is multiplied by Q. And we see it on an example here. This is a 4 by 8 tiling. I made it so that the left carry is the same on the left and on the right. It's simplified what we are going to do. So what is the average of the label on this row? 2. Yes. The number are small. What are the average of the number here? 1. Here is more difficult. 1, 2, 2, 1, 1, 2, 1, 2. So it's about half and half. So the average is 3 half. Here the average, you have 2 zeros, so it's 3/4. And then you have only 1, 2 here, so the average is 9/8. And then you observe that something is happening here. You multiply by 2/3, or by 2, and then by 2/3, by 2, and so on. Okay? What's happening is this. You are looking at, if you look at an infinite tiling, and this was proved in Durand, Gamard, Grandchamp. So in any tiling with these tiles, average is well defined, and the computation follows the map G. So this is almost an exchange of 2 intervals, right? But the slope is not 1. Slope is 2, slope is 2/3. But essentially, it's like a rotation. But more importantly, the proof by Carey was that, in fact, this map G has no periodic orbit. And this was a proof that if there exists a tiling, then it would not be periodic. And a very nice proof, using the fact that the matching rules satisfy the equation. Then, the Janel-Rao tiles, I've been studying it a lot, and I presented it here. If you remember, it was just here. So you have 11 tiles. You have this partition. You can encode a lattice placed anywhere on it. You encode it by the partition, and you get a configuration which is a tiling. So this is very nice. But the end message is the labels of the Wang tile were given by Michael Rao and Emmanuel Jandel. They were formed by computers, like 0, 1, 2, 3, 4. But these labels are not arithmetic values. It's just a set of size 5, let's say. And here, these results say that these tiles are computing something. They are computing the orbit of the +1 on a torus of irrational side. +1 horizontally or +1 vertically. So the question we can ask is, can we replace the matching rules by equations like Carey? Because we see that something like this is happening. The tiles are computing something. Can we see it on the matching rule? That was a question I asked. And also, of course, here golden mean is appearing because the slope is golden mean related. So, of course, this family is not alone. So we want to characterize this family. And then, if you want to characterize this family, like Janel-Rao is very complicated. It has a big pre-period in the SADIC structure. So if we want to look at this question, it's better to look at easier examples. And one example which was forgotten, I think, eclipsed by the Carey example. We always speak about Carey, but never we speak about this. This is a very nice example, proposed by Amann in the 70s. So you have two L-shaped, golden mean everywhere, with these dash edge and solid edge inside. And here the matching rules is that if you want the dash and the solid edge to continue across tiles. So you get tilings like that. And then in the book, there are 4 pictures which are very nice. You remove the edges of the tiles. You get 4 families of slopes, lines. You cut let's say, along the solid lines, you get parallelogram, 16 different, which have dash lines inside. And then you want to tile so that the dash match. Well, you can just encode this into Wang tiles. And here you have 6 labels. 1, 2, 3, 4, 5, 6 is like A, B, C, D, E, F. There's no arithmetic value here, right? But this one is symmetric. By each tile, you have its reverse version. So it's a very nice set to look at. So based on this set, if we look at it better, closely, we can find it belongs to a family, which is takes all message for today. It's the metallic mean Wang tiles. And where do they live? They live there. They are substitutive, but there's a way to see them so that the matching rules satisfy the equation. It's a very nice family, and like the Fibonacci word, which is defined by many ways. It's balanced, it has complexity n+1, it's a mechanical word, it's a fixed point of a substitution, etc. You can do the same with the metallic mean. You can define them equivalently in many ways, and this is what we will do now. Metallic mean Wang tiles. So, it's based on the metallic mean. What is this number? Take the square, do a billiard game where you start from the origin and you draw two balls with angle to the horizontal side, the same as the angle to the vertical side. At some point, you will hit that wall. So you imagine you're on a torus. Right? At some point, you hit that wall. First, if the same speed will hit here. And then the question is, for which slope beta do you hit the same point? So if there is a chalk here, you can write the equation. So it's beta will hit n times, and then what remains is the inverse of beta. So if you multiply by beta, you get beta squared. You get this equation. So this is the equation whose positive root of the polynomial is the metallic mean. So these are the numbers such that their constant fraction expansion is n. Sometimes they are called metallic mean, silver means, or noble means. I call them metallic mean. So these are the tiles. Okay, so you have different kinds of tiles. The first are the white. ij are two integers between 1 and n, and when I write I bar is +1. Okay. So the white tiles, they add +1 vertically and horizontally. And how many white tiles do we have? N squared. And then you have the blue, the yellow, the green, and the anti-green tile. These are horizontal. And basically, they do +1 from left to right, like the I becomes I +1 always. Here it's a mistake. There must be a bar here. Or maybe the bar is on top of the dot. And then what changes is that you have either 0, 1 to 0, 0, 0, 0 to 0, 1, 0, 1 to 0, 1, 0, 0 to 0, 0. And also this changes. You can study this. Anyway, blue, you have n plus 1 of them, yellow, n of them, green, n plus 1 of them, anti-green, n of them. And you have their vertical version as well. So you flip along the positive axis, okay? And then you have the junction tiles. You have 9 of them, and you take whatever choice for the left and top, and a choice for the right and bottom, get 9 tiles. It comes out of nowhere, but it's like this. And then with this, what we have seen before, we define the extended set, Tn prime. The white, the blue, etc. And then the at is the symmetry under the positive diagonal. This I call the extended set. Why? Because we will remove some of them. Because some tiles we don't need. Because sometimes you can show proof is non-trivial. You don't need the anti-green. You can get rid of them. You don't need the last blue tile and the vertical one, horizontal. And one of the junction tiles you don't need. And it's reverse. You remove those, and you call what's remaining the set of metallic mean Wang tiles. How many of them? N plus 3 squared. Because you have 7 junction tiles remaining. You have n plus 1 green, n blue, n yellow, times 2, plus n squared. That's n plus 3 squared. Works for all n. And then maybe you can ask, why do we need this extended set if there are at least 2 reasons, and we will see it in the next slides. So this is an example of a tiling. So the tiling you will see vertical lines and an horizontal stripe of colored. When there's a color, it means it starts with 0. 0, 0 is blue, 0, 1 is yellow. When it goes from 0, 0 to 0, 1, it's a green tile, etc. So you define omega n to be omega tn, the set of valid configuration over these tiles. And of course, this is a subshift, so you can act by translation on it. Let me use this, it's more efficient. So, first theorem is this. T1 is Hamann. This is the proof. So 1, 2, 3, 4, 5, 6 obtained from the whatever are these. 1, 1, 2, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 2, 0, 0, 0. This is a visual proof. So this is Hamann in the same order as in the book of Grandbert and Schaffer. This is the color I put on the tiles, and I reorder them to show it like this usually. Okay, so this is a family which extends the Hamann. Other theorem, it's self-similar. And from this you conclude as a corollary that it's aperiodic. It's minimal. So Janel-Rao is not minimal, Carré is not minimal, Kulik is not minimal, this one is minimal. It's nice. And the inflation factor of the self-similarity is the nth metallic mean. So this is why we call it like this. It's related to the metallic mean. And here a reason why you need the extended set. Very nice. Self-similarity. You want to prove this? You compute the return blocks to the junction tile, because naturally the tiles split along those colored lines, the colored edge. You enumerate what you can see as a return block. They are in bijection with the extended set. So if you get rid of the tiles you don't need, they reappear at the next level. And then they are forbidden, so you get rid of them. And then at the next level they reappear, but they are forbidden, so they disappear and so on. So it's very nice. I like this property. So this is an image of the substitution for n equal 1. So here the substitution is not uniform, but we are reusing a definition of non-uniform morphism that appeared in Moses already. And this substitution is the same as the one you see in the book Grandbert and Schaffer, right? And then when n equal 2, you get this. N equal 3, you get this. N equal 4, etc. Okay? So always the size is n plus 1 for the image of the junction tile, n plus 1 times n plus 1. The image of the white tile are the small ones, so it's n times n. And these are n times n plus 1 or n plus 1 times n, right? Here's another way of defining these tiles. We are computing something. So what is it? Let Vn be a set of vectors in N3, so non-negative, non-decreasing, and I will say V1 is at most 1. Then I define a map which will take as input 2 vectors, Vn, and will output something which may not be in Vn, but it's a size 3 integer. And the map is defined by this. Comes out of nowhere, but it works. Okay, so R0 is U0 always, and R1, R2 will be given by 2 cases depending on the value of U0 and V0. So either you subtract n, or you put 1 here. So this is where you can have negative values here for the output, because you have a subtraction here. And here, this is crazy thing with carry, which is difficult to understand, but this is the easy part. We do plus 1, right? The tiles are computing plus 1. The U2 plus 1, let's say, is the part we can understand easily. And then what do? You construct Wang tiles by defining a computer chip which, given input U and V, will output theta n of UV here and theta n of VU here on top. And then the idea, we want to glue the chip together in such a way that it computes something. So the output needs to match what the input can be. So this adds a restriction on the type of computation. And in fact, it defines a set of Wang tiles. So what is the set of Wang tiles? It's the set of instances of the chip in such a way that the input are in Vn and the output as well. So this is the same set as we have seen before. These are the metallic mean Wang tiles. And here's the proof. It's very nice. Tn is the extended set, again. So you need those extended sets for another reason, is that these are the instances of the computer chip. And some of them you don't need. If you tile arbitrarily large, you get rid of them and so on. Okay, here's another thing you can do. You can think of Sturmian as mechanical sequences. Here also. So you are on the unit square. You define lambda n to be this map of 4 of these linear forms, the 3-dimensional vector. Then you define Tn. For every xy, you define a Wang tile like that, using lambda n. So these are vectors all around. I'm using the fractional part. And what you can show is that if at position ij, you put the tile Tn, where you rotate by beta, horizontally and vertically, by beta or by beta minus 1 is the same, right? Because mod 1 is the same. So I could remove the beta minus 1. But this is a valid tiling with the metallic Wang tiles Tn. In fact, the image of Tn, small Tn, is Tn. So that's another description of this set. But here you don't need, this is only the tiles, not the extended set. And here's an example where you see something which reminds of Carré. So now you will not take the average of these, but you will take the average of the scalar product with D, where D is 0, minus 1, 1. So the difference between the middle entry and the last. So the difference is 3, 3, 3, 3, 3, 3, 3, 3, 2, 2. So the average is 28 over 30. You do this for every line, you look at the average, and you notice that it adds 3 over 10 each time. So the rotation, what is 3 over 10? 1, 2, 3. It's the frequency of columns with color. And here the left and right carry are the same, so it simplifies the observation here. So rotation are involved in the equation. This is, let's say, the main theorem. So given the configuration, you can recover the starting point, xy, doing averages. So given the configuration, let's say the top, use it. Top wi0. So this is a line in the configuration at 0 at the origin, and you look at the top color, it's a vector. You do scalar product with D. It gives a value between up to n plus 1, but n plus 1 you don't see it always. It's a value between 0 and n. You divide by n, it's a value between 0 and 1. The average is well defined because it's well distributed, it's balanced, and the proof. I noticed this morning, in the proof, I found a very nice book, which was exactly the statement I was needing. So I cited it, I said, this is a very nice book, I like it, this is exact. And then this morning I realized that's the book we mentioned yesterday. So it's a very nice book, I agree. So this factor map commutes with the Z2 action by rotation by metallic mean. And that's it. Yes, it's very nice. We can say more because this factor map is almost 1-to-1. This is painful. So the Z2 action by rotation is the maximal equiconstance factor. The factor map is almost 1-to-1, and the factor cardinalities of the factor map is 1 to 8. It's uniquely ergodic, and with this, this factor map is continuous, and in fact, it gives the isomorphism between the two systems seen as measurable dynamical system. I'm just going fast because I want to say other stuff. I think I will have enough time. So if you look at the inverse image of lambda 3, so where do you get those vectors from? These are the places where you get the vectors. If the way this is the pre-image of Tn, the way it's defined, you will need this, and it's merged under the symmetry by the positive diagonal, and then you get the partition. And you can show that if you use this partition to encode the Z2 action, you have this equality. And by you are using the definition of Markov partition for a dynamical system, if this is something which is a subshift of finite type, then we say that the partition is a Markov partition for this dynamical system. So this is what I say here. But remember this partition, we will see it again at the end when we consider stone inflation. So we have a substitution, so we can turn it into a stone inflation and find the Rauzy fractal associated to it. So let's do this. First, we can do it in one dimension, it's easier. So look at this substitution. A goes to A, B, N. B goes to A, B, N minus 1. This is related to metallic mean with the characteristic polynomial in the incidence matrix. What is the most important is the left dominant eigenvector, N beta minus 1. So these are the good shapes for the letters in order that you make this non-uniform substitution uniform. So what I mean by this is this. If you do it with, I didn't have time to do it this morning, so this is for Fibonacci, uniform, you get this image. But if you turn the letter into tile length using the left eigenvector for length, you get a very nice image, like if the substitution was uniform. So this gives position of the left endpoint of intervals, which you can describe, but it's a point set which lives in the algebraic ring. Using this, you can define equation to define the point set. So lambda A is the left endpoint of an interval where you put letter A. Same for B. So where do you put letter A? Well, A always starts, so it's always beta times lambda A union beta times lambda B. With B, you need to translate each time, so 1, 2, 3 times in the image of B of A and 2 times here. Here I'm reusing the construction which is described in the book of Bakke and Grimm. You take the Galois conjugate of the point set and you take the closure. This turns beta into beta star, so it's an inflation which becomes a contraction. And since the sets are closed, using Hutchison theorem, you have a unique solution to this. It's the attractor of this GIFS. And in this case, it's not fractal. There are 2 intervals, -1 beta minus 1 and beta minus 1 beta. So this is the Rauzy fractal here. You can do this in 2 dimensions using a 4-letter alphabet, using the direct product of rho n with itself, and it gives those shapes coming from the left eigenvector. And you see here the shape of the tiles, right? So these are the junction tiles, these are the white tiles, and the stripe tiles. These are the proper length of these tiles when you do them as a inflation. And then you compute the attractor of the IFS for this direct product, you get this. Well, of course, it's the direct product of what we've computed already. This times this, you have 4 shapes. This substitution is a simplification of omega n we have seen earlier. So what if we do the stone inflation for omega n and compute its Rauzy fractal? Well, here's what we get. So it's a refinement of the previous partition. And you see here you have 1, 2, 3, 4, 5, 6, 7. So these are the region associated with the junction tile. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are the white tiles. Here you have the blue, the yellow, and the green, horizontal and vertical, and so on. So this is the Rauzy fractal associated to the substitution. And it's the Markov partition we have seen earlier. Reshaped a little because you go from -1 to beta. And here it's the inverse of beta, instead of 0, 1, which I use to define all the labels of the tiles. Okay, finish with this, one slide. Some open question. So if we come back to Jean-Rau, there must be labels and vectors that allow us to understand these tiles. The same can be done. What is the computer chip associated to Jean-Rau? Which other algebraic number arise in aperiodic tiling? For instance, take Fibonacci substitution, horizontally, vertically, direct product. Using Moses, there exists a set of Wang tiles having the same structure. Compute the stone inflation, the GIFS, the contracting, since it's cubic, this fractal will be 4-dimensional and will be a refinement of the product of two Rauzy fractals. And what will be the shape? Because here we have slope line, which appear for metallic mean, but those slope line maybe will be fractal surface in 4 dimensions, if you want to describe this well. Harder to see. And then the last question is, can we do it reverse? If I give you a metallic mean Wang tiles, are you able to find the shape? Yes, stone inflation. Are you able to find the dash line, the Hammond bar, in such a way that you recover L shapes? Are you able to find the L shapes from the tiles? First, there's just n equal 1, and then n equal 2, 3, 4. I give you the metallic mean Wang tiles. Are you able to find the L shapes or the T shapes or whatever shapes geometrically which will encode the metallic mean Wang tiles? The question I have. I don't know what to do this. I'm done. Thank you.